Welcome! Today, we'll dive into LeetCode problem number 1258, synonymous sentences. In this problem, we'll explore how to generate all possible synonymous sentences by leveraging a given set of synonyms. Let's get started with an overview of the problem and the approaches we'll take to solve it. The problem asks us to generate synonymous sentences based on a given list of synonym pairs and an input sentence. Specifically, we need to replace words in the given sentence with their respective synonyms, as defined by the pairs, to form all possible variations of the sentence. Each word can either remain unchanged or be replaced with one of its synonyms. Importantly, the generated sentences must be returned in lexicographical order, ensuring a consistent and predictable sequence. The input consists of a list of synonym pairs, where each pair defines two words that are considered synonyms, and a sentence expressed as a single string. The output is expected to be a list of all possible valid sentences that can be generated by applying the synonym replacements. To understand this better, let's look at the first example. Here, the synonym pairs are happy and joy, sad and sorrow, and joy and cheerful. The input sentence is I am happy today but was sad yesterday. Using the synonym pairs, we can replace happy with joy or cheerful, and sad with sorrow. This results in 6 variations of the sentence, such as I am happy today but was sad yesterday, I am happy today but was sorrow yesterday, and so on. The output list includes all such variations, sorted in lexicographical order. This ensures that the sentences are returned in a consistent, alphabetically sorted sequence. In this example, we also see that the synonyms form groups. For instance, happy, joy, and cheerful are connected. This means that if we replace one word, we consider all synonymous options within its group. Similarly, sad and sorrow are another group. The goal is to systematically replace each word in the sentence, considering all valid synonyms, and then return the sentences in sorted order. Now, taking a second example, if the synonym pairs are fast and quick and speedy, and the sentence is she is fast, we generate 3 variations, she is fast, she is quick, and she is speedy. Again, the output is sorted lexicographically. Here's another example. If no synonym pairs are provided, like in the case where the sentence is I love programming, the output remains unchanged as I love programming. This is because there are no synonyms to apply, so the input sentence is returned as is. Notice how the presence or absence of synonym pairs directly affects the variations we can generate. The key takeaway here is that the algorithm must handle both cases where synonyms are provided and where they are absent, ensuring correctness in all scenarios. The problem comes with certain constraints to guide the solution. The list of synonym pairs can have at most 10,000 entries, and each pair consists of exactly 2 words. Each word in the synonyms list or the input sentence has a maximum length of 10 characters, and the input sentence itself can have up to 100 characters. The sentence is guaranteed to be well-formed, with words separated by single spaces and no extra spaces at the start or end. All words are composed of lowercase English letters, and there are no duplicate synonym pairs. Additionally, the problem guarantees that every word has at most one synonym relationship, meaning there won't be any cycles in the synonym groups. These constraints allow us to focus on designing an efficient solution that can handle a large number of variations. Lastly, let's consider a few edge cases. For example, if the sentence contains just a single word, the output will include only the variations of that word based on the provided synonyms. If the sentence has multiple words but the synonym groups are disconnected, only the words that belong to these groups will have variations. The problem also ensures that cyclic synonym relationships are not possible, which simplifies the logic for generating the groups. In cases where the input sentence is long, the number of variations can grow rapidly, so efficiency becomes critical. These edge cases highlight the importance of designing a robust solution that can handle a variety of scenarios while adhering to the constraints. To solve the problem of generating synonymous sentences, we start by examining the approaches we can consider. The first approach is the brute force method. The basic intuition here is to go through each word in the given sentence and check if it has synonyms in the provided list. If synonyms exist, we replace the word with all possible synonyms and generate every combination of sentences. The implementation involves using nested loops to systematically try all these replacements for every word with synonyms. However, the main drawback of this approach is its inefficiency. The time complexity grows exponentially with the number of words that have synonyms, making it computationally expensive. Additionally, a lot of redundant work is performed, as the same combinations are effectively recomputed during the process. While straightforward, this approach struggles with scalability, especially for longer sentences or larger synonym groups. A more efficient strategy is the graph-based approach. Here, we treat synonyms as nodes in an undirected graph, with edges connecting words that are synonymous. The key idea is to group words into connected components, where each component represents a set of words that are all synonymous with each other. For implementation, we first build the graph by treating each synonym pair as an edge. Then, we use an algorithm like UnionFind or BFS/DFS to identify the connected components in the graph. Once the components are identified, generating sentences becomes straightforward. For each word in the sentence, we replace it with all the words in its connected component, or use the word itself if it has no synonyms. Backtracking is then used to systematically generate all possible sentence combinations. This approach is significantly more efficient. The graph construction itself has a linear complexity relative to the number of synonym pairs and unique words, and the sentence generation step avoids redundant recomputation by leveraging the connected components. This method is not only faster but also scales well, even for large inputs. The graph-based approach is the strategy we chose because of its efficiency and scalability. One of the key observations here is that synonym relationships naturally form connected components in a graph. For instance, if happy is synonymous with joyful, and joyful is synonymous with cheerful, the three words form a single connected group. By grouping synonyms in this way, we can efficiently map each word in the sentence to all possible replacements. This insight simplifies the problem into two primary tasks: identifying the connected components within the graph and using those components to generate the sentence combinations. The breakthrough or aha moment for this approach is realizing that graph theory provides a direct and elegant solution to what initially seems like a combinatorial explosion of possibilities. By focusing on graph construction and leveraging the structure of connected components, this approach avoids redundant computations and handles large synonym groups with ease, making it the most effective strategy. While the graph-based approach is optimal, it is important to consider its trade-offs. One minor downside is a slightly higher pre-processing cost due to the graph construction step. However, this overhead is negligible for larger inputs because of the overall efficiency it offers. In comparison, alternatives like brute force or recursive DFS directly on the sentence text are far less efficient and do not scale well. To implement the graph-based method, we follow 4 key steps. First, we build an undirected graph using the synonym pairs. Second, we use UnionFind or BFS/DFS to identify connected components of synonyms. Third, we map each word in the sentence to its corresponding connected component and use backtracking to generate all possible sentence combinations. Finally, we return the sorted list of these generated sentences. This approach ensures correctness, efficiency, and scalability, making it the optimal solution for solving the synonymous sentences problem. In this problem, the objective is to generate all possible synonymous sentences based on a given sentence and a list of synonym pairs. These synonym pairs can be visualized as an undirected graph, where each word is a node and an edge exists between two nodes if the words are synonyms. By traversing the connected components of this graph, we can group all interchangeable words together, which simplifies the process of generating synonymous sentences. For instance, consider the synonym pairs happy, joy, elated. Here, happy, joy, and elated form a connected component, meaning these words can be used interchangeably. Representing synonyms as a graph helps us efficiently manage these relationships and is the foundation of the solution approach. To work with the graph, we perform connected component analysis using either depth-first search or breadth-first search. This allows us to identify all groups of synonymous words. Each connected component is stored in a dictionary, where the key is a word and the value is the entire set of words in its component. For example, if we start with the word happy, its connected component would be happy, joy, elated. Once we have the connected components, the next step is to process the input sentence. We split the sentence into individual words and check if each word exists in the graph. If a word is found in the graph, we can replace it with any word from its connected component. If it's not found, the word remains unchanged. For example, the sentence I am happy is tokenized into I am happy. The word happy is part of a connected component, so it can be replaced with its synonyms, while I and am remain as they are. Now, to generate all possible synonymous sentences, we use a backtracking approach. Starting with the first word in the tokenized sentence, we check if it has synonyms. If it does, we iterate over all synonyms, recursively proceeding to the next word. If a word doesn't have synonyms, it is added to the sentence as is. Once all words in the sentence have been processed, we append the completed sentence to the results list. For example, given the words I am happy and the synonyms for happy, happy, joy, elated, the generated sentences would include I am happy, I am joy, and I am elated. The recursion ensures that we explore all combinations systematically. Additionally, by utilizing the pre-computed connected components, we can retrieve synonyms in constant time, making this approach efficient. This algorithm incorporates several key insights to ensure correctness and efficiency. Representing synonyms as a graph simplifies traversal and makes synonym lookups efficient. Connected component analysis groups all synonymous words together, even when they are indirectly related. Backtracking guarantees that all possible sentence combinations are explored systematically. By pre-computing connected components, we avoid redundant computations during sentence generation. The primary data structures used include an adjacency list for the graph, a dictionary for connected components, and a list to store the generated sentences. In terms of complexity, graph construction and connected component analysis each take O, V plus E, where V is the number of words and E is the number of synonym pairs. Sentence generation has exponential complexity in the worst case, as it depends on the number of synonyms per word and the sentence length. Sorting the results takes O, M asterisk log M, where M is the number of generated sentences. There are also several edge cases to consider. If the sentence contains no synonyms, such as I am unique, the output is simply the original sentence. Words not present in the synonym pairs are treated as is, without modification. For large synonym groups, the graph traversal ensures correctness and avoids redundant computations. If the synonym list is empty, no replacements occur, and the input sentence remains unchanged. This approach effectively combines graph theory and backtracking to generate all possible sentences systematically while ensuring efficiency. By leveraging connected components, we streamline synonym lookups and minimize computational overhead. This guarantees that the solution is both robust and scalable, even for complex scenarios. Here, we're implementing the solution to generate all possible synonymous sentences. First, we import the necessary modules, defaultIC to create a graph structure and DEEC for efficient breadth-first search. In the Generate Sentences method, we start by constructing a graph where each synonym pair is bidirectionally connected. This allows us to map each word to its related synonyms. Next, we define a get_synonyms function that uses BFS to traverse the graph and find all synonyms connected to a given word. If the word is not in the graph, we simply return the word itself as a set. During the BFS, we maintain a visited set to avoid cycles and a queue to process words level by level. The result of this function is the complete set of synonyms for the input word. Finally, we prepare to map each word to its corresponding synonym set by declaring an empty dictionary, word_to_synonyms. Now, we populate the word_to_synonyms dictionary. For each word in the graph, if it hasn't already been processed, we retrieve its synonym set using the get_synonyms function. Then, for each synonym in the set, we map it back to the same synonym group, ensuring all related words point to the same set. Next, we split the input text into individual words and define a backtracking function to generate sentences recursively. The backtrack function takes the current index and builds sentences word by word. If we reach the end of the word list, the constructed sentence is added to the result. For each word, if it has synonyms, we iterate over them in sorted order, appending each to the current sentence and continuing the recursion. If no synonyms exist, we simply add the word as is. Finally, we call backtrack starting at index 0 with an empty sentence and return the generated sentences. Here, we begin by defining the main method generate sentences, which takes a list of synonym pairs and a target string text. The first step is to build a graph representation of the synonyms. We use a hash map where each word is a key, and its value is a list of words that are directly synonymous with it. To populate this graph, we iterate over each pair of synonyms, ensuring that both words are initialized in the graph and then linked to each other by adding them to each other's adjacency list. Once the graph is constructed, the next step is to identify all connected synonyms for each word using either BFS or DFS. For this, we maintain another map, word to synonyms, where each word is associated with a set of all its synonyms, including indirectly connected ones. If a word has not been processed yet, we perform a depth-first search to find all synonyms in its connected component and store the result in word to synonyms for all the words in that component. Now that we have mapped every word to its full set of synonyms, the next step is to generate all possible sentences using backtracking. First, we split the input text into individual words using text.split, and initialize an empty list called result to store the final sentences. The backtrack method is then called, which recursively builds sentences by replacing each word with all its synonyms, if available. The DFS method, included here as well, ensures that we can explore all connected synonyms during graph traversal. It avoids revisiting words by checking and marking them in the visited set. The backtrack method operates by checking each word in the sentence. If the word has synonyms in the map, it tries each synonym in turn, adding it to the current sentence, and proceeds to the next word recursively. If the word has no synonyms, it is simply added as is, and the recursion continues. When the final word is reached, the constructed sentence is added to the result list. Finally, inside the backtrack method, we handle the recursive exploration of synonyms. If the current word exists in the word to synonyms map, we retrieve its synonyms, sort them lexicographically to ensure the sentences are generated in sorted order, and iterate over each synonym. For each option, we add the synonym to the current sentence, recursively call backtrack for the next word, and then backtrack by removing the last word to restore the state for the next iteration. If the current word does not have any synonyms, we simply add it directly to the sentence, continue to the next index, and backtrack as usual. This approach guarantees that all possible sentences are explored and added to the result list. Ultimately, the program returns the result list containing all valid sentences formed by replacing words with their synonyms wherever applicable. In this example, we are starting with a basic set of synonyms and a simple sentence to understand how the solution works. The input provides two synonym pairs, happy and joyful and cheerful. First, we need to build a graph representation of these relationships. Using an adjacency list, we connect each word to its direct synonyms. For example, happy is connected to joyful is connected to both happy and cheerful is connected back to joyful. This graph will help us understand the relationships between the words. Next, we use breadth-first search, or BFS, to find all the words connected in this graph. For happy, we discover the set of connected words, happy, joyful, and cheerful. Similarly, joyful and cheerful are part of the same set. This process ensures that all synonyms are grouped together, even if they are indirectly connected through other words. After identifying the connected groups of synonyms, we map each word to its respective synonym set. This creates a clear mapping where, for example, happy, joyful, and cheerful all point to the same group. This mapping allows us to quickly retrieve all possible synonyms for any word in the text. Now, we start generating sentences by processing the input text. For the sentence I am happy, we handle each word sequentially. Words like I and am are not found in the synonym map, so we append them directly. When we reach happy, we see that its synonyms are happy, joyful, and cheerful. Using these options, we generate three possible sentences: I am happy, I am joyful, and I am cheerful. This process ensures that we explore all valid substitutions for the given text. Finally, we collect all the generated sentences, which in this case are I am cheerful, I am happy, and I am joyful. These sentences represent all lexicographically sorted combinations of the synonyms. In this second example, we are working with multiple groups of synonyms, which makes the problem slightly more complex. The input provides two separate groups, one connecting fast, quick, and speedy, and another connecting smart and intelligent. The sentence to process is the fast and smart fox. As before, we start by building the graph. Using the synonym pairs, we create an adjacency list where fast is linked to quick, quick is linked to both fast and speedy is linked back to quick. Similarly, smart is connected to intelligent, and intelligent is connected back to smart. Using this graph, we use BFS to find the connected components. Fast, quick, and speedy form one group, while smart and intelligent form another. These connected groups allow us to map each word to its respective synonym set. For instance, fast is mapped to the set fast, quick, and speedy, while smart is mapped to the set smart and intelligent. Once the mappings are complete, we process the sentence, the fast and smart fox. Starting with the first word, we see that it is not in the synonym map, so we append it directly. For fast, we find its synonyms in the set fast, quick, and speedy. We then explore all possible substitutions for this word. Next, we process and, which is also not in the synonym map, so it is appended as is. For smart, we find its synonyms in the set smart and intelligent and explore all possible substitutions. Finally, the word fox is not in the synonym map, so it is appended directly. By combining these options, we generate all possible valid sentences. The results include the fast and smart fox, the fast and intelligent fox, the quick and smart fox, the quick and intelligent fox, the speedy and smart fox, and the speedy and intelligent fox. This covers all combinations while preserving the structure of the original sentence. The final set of sentences for this example is, the fast and intelligent fox, the fast and smart fox, the quick and intelligent fox, the quick and smart fox, the speedy and intelligent fox, and the speedy and smart fox. Each sentence represents a valid substitution based on the provided synonyms. Now, let's consider a simpler case where no synonyms are provided. If the input contains no synonym pairs, the graph remains empty, and there are no connected components to find. For the text hello world, we simply process each word sequentially. Since neither hello nor world has any synonyms, they are appended directly to form the final sentence. In this case, the result is simply hello world. This demonstrates that the algorithm handles edge cases where no synonyms are present. To summarize, the solution works by first constructing a graph to represent synonym relationships, then identifying connected groups using BFS. Each word is mapped to its corresponding synonym set, and backtracking is used to generate all possible sentences by exploring substitutions for words with synonyms. The results are then sorted to ensure they are returned in lexicographical order. This approach efficiently handles different scenarios, from sentences with multiple synonym groups to cases where no synonyms are present. The combination of graph construction, BFS for connected components, and recursive backtracking ensures both correctness and completeness in generating synonymous sentences. Here, we analyze the time complexity of our approach. First, we build the graph from the given synonym pairs. For each pair, we add both words to each other's adjacency list, and since there are m pairs, this step has a time complexity of O(m). Next, we perform BFS to identify all connected synonym groups. In the worst-case scenario, if all the words are part of a single connected component, BFS will traverse all n unique nodes and m edges, resulting in a total complexity of O(n plus m) for this step. After that, we map each word to its respective synonym set, which involves iterating through all nodes in the graph, leading to a time complexity of O(n). Finally, during the sentence generation phase, we use backtracking to explore all synonym combinations. If the input text has L words and the synonyms for each word form sets of sizes K1, K2, KL, the complexity of generating all possible sentences is O, K1 asterisk K2 asterisk, asterisk KL. Additionally, sorting each synonym set incurs a cost of O, key asterisk log, key, for each set, summing up to O, sum, key asterisk log, key, for all sets. By combining these steps, the overall time complexity is a combination of these terms. The total time complexity calculation simplifies to O, m plus n plus n plus m plus sum, key asterisk log, key, plus K1 asterisk K2 asterisk, asterisk KL, which can be further reduced to O, n plus m plus sum, key asterisk log, key, plus K1 asterisk K2 asterisk, asterisk KL. Now, considering the space complexity, the adjacency list used for graph storage takes O, n plus m, space, as it depends on the number of nodes and edges. During BFS, we also maintain a visited set for each connected component, which in the worst case requires O, n, space. Additionally, we create a mapping from each word to its synonym set, which requires space proportional to the number of words and the average size of synonym sets, resulting in n*k_average. For backtracking, the recursion stack depth equals the number of words in the input text, L, and at each level, the memory used depends on the branch sizes, leading to a space complexity of L*k_max, where k_max is the largest synonym set size. Finally, we store all generated sentences. If there are k1*, k2*, *kl sentences and each sentence has L words, the storage cost becomes O, k1*, k2*, kl*, L. Combining all these components, the overall space complexity sums up to O, n plus m plus n *k_average plus L*k_max plus k1*, k2*, kl*. Comparing our optimized approach to a naive brute force method highlights the efficiency of pre-processing. A naive approach would generate all possible sentences by directly substituting each word with its synonyms, leading to a time complexity of O, k1*, k2*, kl, for sentence generation but without any pre-processing to streamline the process. In contrast, our optimized approach reduces redundant computations by pre-processing the synonyms. By using BFS to identify connected components, we avoid repetitive synonym lookups and ensure that generation is more efficient. While this pre-processing step introduces an additional cost of O, n plus m, it significantly reduces the overhead during the backtracking phase. Overall, this balance between pre-processing and generation allows our approach to scale better for larger inputs, making it far more efficient than naive methods. When working on this problem, there are several common mistakes to watch out for. First, not building the synonym graph correctly is a frequent pitfall. If you treat the synonym pairs as an unstructured list instead of constructing a proper graph or using a union-find structure, you might miss important transitive relationships. For example, if happy is connected to joyful and joyful to elated, you'll need to ensure that happy is recognized as synonymous with elated as well. Another mistake is mishandling circular dependencies. Cycles in synonym relationships can create infinite loops during traversal, which can lead to runtime errors or recursion depth issues. Lastly, inefficient sentence generation is a critical error. If you rely on brute force methods to generate all possible sentences without leveraging the graph structure, you'll end up with redundant computations and poor performance, particularly with long sentences or a large number of synonyms. These issues can significantly impact your solution's efficiency and correctness. Now, let's look at some additional pitfalls. Failing to handle edge cases is another common issue. For instance, an empty sentence should return an empty list, and words in the input sentence that don't have any synonyms in the provided pairs should remain unchanged. Ignoring these conditions can lead to runtime errors or incorrect outputs. Another critical issue is not adhering to the requirement for lexicographical order. The problem explicitly states that the generated sentences must be sorted. Skipping the sorting step will result in failed test cases, even if the generated content is correct. Paying attention to these details ensures your solution is both robust and meets the problem's specifications. This problem is also a great opportunity to showcase your understanding of key concepts during interviews. For example, it tests your ability to implement graph traversal techniques like depth-first search, breadth-first search, or even union find. You should be prepared to discuss the trade-offs between these approaches. If you use union find, interviewers may ask about optimizations like path compression or union by rank, which make the solution more efficient. Additionally, lexicographical sorting is often a follow-up question if it's not addressed in your initial implementation. It's also important to be able to analyze time complexity. For instance, building the graph typically has O, n, complexity, while generating sentences depends on the branching factor, which is determined by the number of synonyms per word. Lastly, you might be asked how to adapt your solution for real-world scenarios, such as handling larger datasets or dynamically updating the list of synonyms. It's helpful to draw connections between this problem and similar ones, as these relationships can deepen your understanding. For example, LeetCode 721, Accounts Merge, involves grouping related entities using union find, which is conceptually similar to grouping synonyms. LeetCode 399, Evaluate Division, requires handling transitive relationships in a graph, much like determining synonym chains. LeetCode 47, Permutations 2, focuses on generating unique permutations, which aligns with the idea of creating distinct sentence variations. Lastly, LeetCode 1202, smallest string with swaps, involves grouping characters into connected components and sorting them, which parallels the process of managing synonym groups and ensuring lexicographical order. Exploring these related problems can enhance your problem-solving skills and prepare you for variations of this challenge. There are also several alternative approaches you could explore depending on the constraints and requirements. A depth-first search with backtracking involves building a graph where each word points to its synonyms and using DFS to generate all possible sentences. This approach is straightforward and works well for small inputs, but it can lead to Stack Overflow for deep recursion or very large sentences. Another option is using Union Find to group synonyms into connected components. This method efficiently manages synonym relationships and avoids redundant computations, though you'll need an additional sorting step to ensure lexicographical order. Finally, a breadth-first search for sentence generation explores all possible sentences level by level. This avoids recursion depth issues and can be easier to debug, but it may require more memory to store the queue. Choosing the right approach depends on the trade-offs you're willing to make in terms of simplicity, efficiency, and memory usage. Great job! In this session, we explored how to tackle the synonymous sentences problem using graph-based techniques. We covered the problem, the solution approach, and the key takeaways. Thanks for joining. Be sure to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!